Okay, so today we are going to go over the multiple linear regression, which is an extension, a simple linear regression. It's more general compared to the simple linear regression. Look at this example and try to come up with an idea about what is this about. Suppose that you are a consultant and you are hired by a client to investigate the association between the sales and the advertising. So you are hired to do two things, or actually one big thing, which is the association between the advertising and the sales of a specific product. The advertising data contains the sales in thousands of units. So we are measuring the sales in terms of quantities. We have quantities. We have 200 different markets. Also, we are budgeting the advertising budgeting this client in dollars, in thousands of dollars for the product in each of the markets. And they have three different media. So they want to put money on TV, on radio, and a newspaper. And they are willing to say or to come up with the idea, okay, how much I'm going to, or how many units I'm going to sell if I put some money on each of these medias. So they want to study the relationship between these predictors and the response variable. We have three predictors because they're putting money on the TV advertising, they're putting money on the radio advertising, they're putting money on the newspaper advertising. And they would like to predict the sales. Okay. When you study the association between two variables or more than two variables, so here we are studying the association between the advertising and sales. So the sales is my response. I'm trying to find the relationship between the sales and TV advertising, radio advertising, and newspaper advertising. Okay, newspaper. All of these are independent variables. If you are willing, or if the client is willing to study the relationship or the association between the sales and the TV advertising, this is a simple linear regression because we have one response variable, one predictor. So all of these guys are predictors, independent variables, independent. Okay. So if the client is willing, again, to study the association between sales, the response, and one of these, then we are talking about simple linear regression. But if we are studying the relation between one response variable and more than one predictor, then we are talking about multiple linear regression. The question is how to study the association between these variables, the sales versus budgets, advertising, some media. We're going to follow some steps. The first step we are going to do is we are going to conduct exploratory analysis. First, we are going to study or visualize the relationship between the response variable, the sales, versus TV advertising, sales versus paper advertising, sales versus radio advertising. So we're going to visualize and assess the relationship. Have something positive, something negative? Do you have something strong positive, strong negative? Is it kind of a straight line? Is it kind of a curvy relationship or what? After we look at the scatter plot, at the same time, we're going to look at the correlation matrix. The correlation matrix is going to tell us, mathematically, it's going to quantify technically, it's going to quantify what we have seen visually. So we're going to look at the correlation matrix and we're going to calculate, basically, we're going to calculate the Pearson correlation coefficient. And we are going to look at the Pearson correlation coefficient between every response versus the predictor. There is a number. It's a quantifiable number. Okay. Because remember, because we work on a sample, this is a sample, we have to look at if this relationship that we are going to get from the correlation, is it significant or no? Is it like or unlikely to be because of the random sampling or? So this is a question that we want to answer first. For that, we would like to look at the relationships between the predictors themselves, how they are interacting together. Because I'm going to put money on radio, money on TV, and money on a newspaper. So what is the relationship between all of these guys? We're going to study something called multicollinearity. After that, when we explored the relationship, I like to put this relationship into mathematical equation. So before doing that, we have to know what variables we have to include in that equation. We know the responsive variable, which is the dependent variable, which is in this case the sales. Also, we know the independent variables. We have 3 of them, the predictors. We're going to put them together about the sample. Then we are going to have sample. Already we did that. So this stage actually obtained the sample data from here. So this doesn't belong to this stage. It belongs up there. After that, we are going to build the model or the equation, because we somehow believe that there is kind of association between the sales and the money that we are going to invest in advertising on the 3 different medias. The equation is going to be something like this. It's going to be the sales is approximately equal beta note, not beta, sorry, B note plus B1 X1. It could be the TV. We can just, X1 is the TV, for example, plus B2, X2 is going to be like the newspaper, plus X3 going to be the X3, which is X3 is going to be the radio, let's say, right? So after we build the model, we are going to interpret the R squared. I'm going to speak about this, which is what is the variation of the models, what is the variation of Y that is explained by the model. Also, we are going to interpret the coefficients B's, B naught, B1, B2, because these have meanings. After doing that, we are going to conduct the most important stage or phase, which is the model diagnosis. We're going to test some of the theories. The first question that we would like to answer is overall model significance or no? Can we rely on that model? Can we use it? To do that, we are going to look at the F test, the F value. We are going to have the null hypothesis. The betas are all 0. Beta 1 equal beta 2 equals. So betas are the coefficients that these are coming from the population model. The B's, these are the one that comes from the sample. Actually, this equation we are going to create because we cannot access the population, but we are studying the hypothesis on the population. That's why we're using betas, not B's. But the values we are getting, which is from the sample, these are the estimates of the betas. Okay, I'm going to talk about this also in a second. We are going to first look at the overall model. Is that something significant? Can we rely on that model? Can we use it? We look at the F test. Also, we are going to look at how much of the variation of the Y is explained by the model, which is the adjusted R squared. Why adjusted R squared? Don't use R squared. We use the adjusted because we have more than one predictor. If you have more than one predictor, it's better to report the adjusted R squared, because R squared, every time you add a predictor to the model, it always stays the same or increase. So to account for adding more predictors, we are using adjusted R squared, because it's not necessarily adding new predictors is going to improve the model. This is wrong. So that's why we're using this adjusted R squared. So that we're going to look at, is every individual variable significant or no? Significant or no? Model is significant doesn't mean that all of the variables are important to the model. Some of them, they are not important. Or they are not significant, means they are just happening by chance. So we can take them out probably. Also, we're going to look at something called the standard error of the estimate. Far you are from the prediction. Too small or too big? If it's small enough to us, practically, then we're gonna, accept that one. After that, we are going to look at the multicollinearity, and we're going to talk about this also. Multicollinearity, when we have relationships, associations between the predictors, because we know this from here, we're going to investigate. Then we're going to look at 2 other issues, the outliers and the leverage point, or points, or influential outliers, we call them. And we're going to look at a measure called Cox-D as well. Finally, we're going to look at the assumptions and see if the assumptions are met or no. And if we have outliers, for example, and an influential observation, do we need to take it out or leave it? If it's influential, probably we are going to think about taking it out. If it's just regular outlier, we may keep it if it doesn't have that impact. Then we are going to look at the assumptions again. If we have issues with the assumptions, then we have to reconsider. The one that we can lean about is the normality. that we have to be strict about is the equal variances or independence or linearity. We have to take some actions. If these are violated, what kind of actions we do? We either add more terms to the problem. Probably we're going to add another predictor, or maybe we are going to add action term, quadratic terms, or some other terms that may help improve the model. Or probably we're going to do some transformations. These are things that we think about later. Finally, we may use the model selection method to give us the very best model based on criteria that we are specifying. So let's start with the first step, which is I'm going to divide these into multiple videos. So the first one I'm going to go over is the descriptive analysis here, or exploratory analytics. So let's go and do some of the correlation. So here, number one, I'm going to study the correlation. I'm going to study the correlation between the response variable versus others, the predictors. So the correlation, I have my data already uploaded. The analysis variables are all of them. I'm going to look at options, select statistics, display p-value, yes. Correlations, yes. Type of plots, matrix of scatter plots, and include histogram. This is enough. So at the beginning, we would like to look at the sales versus TV, sales versus TV, sales versus radio, sales versus newspaper. This is the matrix equation. So the sales versus TV, it's obvious that it's from our sample, it seems that we have a positive, kind of a strong relationship. The same is applicable to the radio with less strength. For sales versus a newspaper seems to be scattered around. So we don't see it. To quantify these, we look at the matrix. Sales versus TV, about 80%, which is a strong positive. TV increases as we put money on the TV, sales are more. And this relationship is significant. So it's unlikely to be due to the random sampling. It's applicable to the radio. It's about 60%. It's positive, high, or medium. It's significant because it's less than 0.05. The newspaper is positive, and this is still okay, weak to moderate, fine, but still it's significant as well. It's unlikely to be due to random sampling. So these are the first impression, the first thing that we have to write down. What are the hypotheses for these? We know the correlation coefficients, these numbers, these are, let me just write one of them. This is little r radio. So sales versus radio, let's say this is 0.57, and this is significant. What are the hypotheses for the R is the sample correlation. But when we do hypotheses, we don't testing for the samples, we test for the population. What is the population corresponding letter for the R? I mean, R is the sample Pearson coefficient. Corresponding one is rho. This is the population. This is the population coefficient, correlation coefficient. So here what we say there is no relationship, no association in sales. Let me put this down. Oops. Between sales and this is radio. Next, alternative hypothesis is we do have an association. There is association, not zero. Or if you like, you can say greater than. It's a positive association. There is a positive. It's a what's so-called positive. It's a one-tailed test. There is a positive association between radio and sales. And these are to the population. So there is a positive association between the sales and radio. We're talking about the population here. Okay. So in this case, we reject the null hypotheses to each node, and we believe that there is significant association between the sales and radio. So we have to repeat all of these for every individual versus the sales. Okay. After that, what we are going to do, we are going to move on to the next step, which is the model specification. So we believe that there are some kind of associations. So you have to build a mathematical model that connects the response with the predictors. Why is that? Why do we need to do that? Because we would like to do some description or a prediction. We would like to predict the sales based on the units based on the money that we're going to put on advertising for each media. So the next we're going to specify the model, and we know this, that we have to write this down. The dependent variable is the sales, the independents are the three others we talked about, and the goal is to study the association between, and which one. The question can be the generic question here. The generic question or the goal is to know what are the best predictors or the significant predictors to the variation of the sales. Or what are the significant predictors to the variation of the sales? One of the questions that we may ask. This is the generic question that we want to ask and answer. Or what is the best predictors to the sales? After that, we are going to build the model. And the very simple model that we are going to build at the beginning, we're going to assume that the population model look like this. Is going to be y is equal beta naught, beta 1, TV, let's say TV, plus, actually it depends which one we're going to place first. Beta 2 radio plus times, these are times, by the way, times beta 3 newspaper. And this is sales. So the population model, we have an epsilon here, the error. In reality, we cannot say the sales equal only these, because there are some error left. We don't know what other variables that may impact or may add effect whatever the sales. So that's why we add the error term. But the sample model, we have the estimated sale. The estimated, because we are estimating sales, is equal not beta 1, because we don't know beta zeros. We don't know the original population 1. We just take a sample. So we are trying to estimate beta naught, which is B naught. This is B1, this is B2, and this is B3. And we don't have the error term. So the estimated sales is literally, we call it Y hat, okay? Model. Let's build the model and see how it goes. We save this. So what we do, we go to the linear regression. The dependent is the sales. Then we have classification variables. Classification mean categorical variables. We don't have categorical variables. We have continuous. All of them are continuous. So I'm going to place them in the continuous. I think I place TV first, radio, then newspaper. Then I'm going to go to the model. I'm going now to build the model. I'm going to add TV, radio, newspaper. I'm going to add them as a single effects. TV, newspaper, as they are. We don't know what kind of, can we come up with something? Can we add more? If you want to add more terms, we can do this from here, but not now, because now we add just the predictors, the raw predictors as they are. Then I'm going to go to options. The confidence interval, I'm going to keep it levels 95%. Look at this. I'm going to look at the collinearity analysis, VIF, heteroscedasticity. We have the diagnostics already, so I'm going to keep this. Panel of plots, I'm going, let me, residual versus each explanatory variable, and do this. Look at what we have then. In the selection method, I'm going to leave this right now. I'm going to get back to this later. But now let me run and see what I get. Okay, I don't want this. Let me take it off. Let me take this off. Where the option selection? It's here. Let me take it off. Let me run again. So let's now go back to the Word document, okay, and see what kind of things we have to do. First thing, let me go. Where is it? Model specification done. Now we would like to construct the regression equation. So let me construct the regression equation. I'm going to copy this. The estimated sales is equal to beta naught. Where is beta naught? Is the intercept. We look at the estimates here. This is 2.9. This is 2.9. 3. By the way, 3 small digits is okay. This is 9. Beta 1 is for the TV. We have 0.0458. The radio, we have 0.189. The 3, negative, so negative 0.001. So this is our estimated model. This is our equation. Then we are going to look at the R squared before we do any diagnostics. So the R squared is equal to 0.9889, 90%. So 90% there it's we have so let me write this down. R squared is about approximately 90%. So there is about 90% the variation of the sales explained by the model. So adding these variables, the three of them to the model, explains a really high number of the variation of the estimated sales, And this is high number. Initially, this is a high number, okay? Then we're going to answer the following because we said we first model building, we would like to so-called look at the the interpretation of the betas, right? So what are the betas? We look at the betas, and this is a critical point. The first beta, the estimators of the betas, which are the B's. So this is for the TV, right? So the TV, we have B1 approximately equals, let me use B, 0.0458. What does this mean? This is a very simple mathematical concept. This is slope. Slope in mathematics mean delta y over delta x. So the change of y over the change of x is over 1, right? So the change of sales over the change of the TVs. So for every additional, these units are in thousands, remember, so this means $1,000. For every additional $1,000 spent on TV, the average sales are estimated increase because it's positive. This is a positive increase. Multiply this by 1,000 because these are in thousands of units. So multiply by 1,000. So we're going to increase the units about 45.8 units. We have to add a few sentences after that. This is, we call it the partial effect because put all of these together into the model, TV, radio, newspaper, translating this. While we are holding radio, we are freezing the effect of radio and newspaper, freezing them. So holding the radio and the newspaper constant. So without taking the account the radio and newspaper into the model, just hold their effect. Let's focus on the TV effect only on the sales. So for every 1,000 we spend on the TV, the average sales are estimated to increase 45 units. With holding the radio and the newspaper constant without considering them, without counting for them, okay? We're separating their effect. And we are going to repeat this for everyone. For the radio is the same. For the newspaper is the same. We're going to just do the interpretation for all of them. After that, we're going to do the model diagnosis. And I'm going to pause this video. I'm going to start the diagnostic in the next video because it's going to be a very long one. Thank you.